Welcome to your last section in Chapter 9. In this section, we are going to continue to look at inference for distributions of categorical data. In this section, we're going to be comparing conditional distributions in a two-way table. Remember, our goodness of fit was only a one-way table, which was a single row. We're going to be able to state appropriate hypothesis and compute expected counts for a chi-square test based on data in a two-way table instead of just a one-way table. We'll compute the chi-squared test statistic, understand how to find the degrees of freedom, and the p-value for the chi-square statistic. We'll perform a chi-square test for homogeneity, a chi-square test for independence, and understand the difference between the two. Then we will choose the appropriate chi-square test in order to answer the question. So if you'll notice, at the end of this lesson, we will have three types of chi-square tests. One for homogeneity, one for independence, and one for goodness of fit from our previous lesson. Let's take a look at what exactly a chi-square test is going to look like for homogeneity and independence. The two sample Z procedures we used in section 9.1 and 9.2 allow us to compare the proportions of successes in two populations or for two treatments. What if we want to compare more than two samples or groups? So more generally speaking, what we're taking a look at is we're looking at the distributions of a single categorical variable across several populations or treatments. So in order to do this, we need a new statistical test, and this test is going to start by presenting the data in a two-way table. And what this means is we would just be taking a look at, for example, the number of people with blue hair across several populations, which would mean maybe for those in Canada, maybe those for them in the United States, and in for Mexico. So that would be a categorical variable, seeing how the counts are related in three different countries. Two-way tables have more general uses than comparing distributions of a single categorical variable. They can also be used to describe the relationships between two categorical variables, basically checking to see if one variable influences another. So let's take a look at the differences. What kind of tests can we use to compare two or more proportions or an association between a row and a column variable? That's going to be the key here. Both of your tests for homogeneity and independence are going to have two-way tables, but we are going to be checking to see whether or not we're looking to see if the distributions across maybe three countries are the same, or there's an association between the row and the variable. So let's take a look at our three different chi-square tests. A goodness of fit test is going to allow us to determine if a specified population distribution seems valid. So does the single line or single row match what our observed is? It will always be single row. We're just checking to see if what we observed matches what we should have gotten. So are the colors of M&Ms in your bag the same as what the company claims? Now let's take a look at what a test for homogeneity looks like. This is different because we are going to be comparing two or more population proportions or distributions, basically counts of a categorical variable. It's going to allow us to see if there is a difference in the distribution across several proportions or several populations. So is the distribution of blue hair the same or different for three populations, the United States, America, and Mexico? The key here is that you're going to have multiple populations. So be very careful with that. Homogeneity also always has to have more than one population. So, for example, here is the same color distribution, the same for all types of M&Ms, regular, peanut, or crispy, or minis. So, for example, that's going to be four populations, regular, peanut, crispy, and minis. Now, a test for independence will determine if one distribution of a variable is influenced by another distribution. This is going to be a single sample, and basically we will take that single sample and break it up and see if two variables within that single sample influence each other. So the key here with homogeneity is going to be two separate populations. Independence is just going to be one population. So individuals in the sample or your single population are classified according to two categorical variables. So for example, I would take a simple random sample of 50 students at your school. I would break them up into male and female and determine whether or not they like to take history or math. So I'd be comparing class they like to take, that's one categorical variable, to male or female, another categorical variable, but it's still one individual sample. Okay, so let's take a look at more of what a test for homogeneity and a test for independence look like. These two tests are similar to the difference between two sample and matched pairs. However, remember with a chi-square test, there are no confidence intervals. So what assumptions and conditions are we going to need to run this test for homogeneity and test for independence? Here's your assumptions and conditions. They're going to be very similar as your assumptions and conditions from your chi-square test for goodness of fit. Number one, we need to have a simple random sample. So we need to make sure that my samples are independent and they're random. Now, this condition is the same as what we've talked about for goodness of fit. So all expected counts are greater than 5. Remember, we're never going to say a chi-square is approximately normal because the chi-square distribution is always skewed to the right. Then your third one is independence. So that either both populations for a chi-square test for homogeneity or independence, or each person is chosen individually. So for homogeneity, the individuals do not influence each other. So you have two separate populations. Now, for your test for independence, we're still going to use the 10% rule. The population is 10 times the sample size. And why are we doing that? Because this is only one sample. Homogeneity is going to be two samples. The first step in the overall test for comparing several proportions or distributions is to arrange your data in a two-way table. So a two-way table just means I have two rows and or more than one row and at least two columns. So think of the counts. We're going to be using matrices. So think of the counts as the elements of a matrix with my rows as my R is my rows and C as my columns. So it's going to be called an R by C table. So R is just your number of rows, C is your number of columns. So it has R times C cells. So what exactly will the hypothesis look like? Now remember, with homogeneity, we have two populations and we're checking to see if the distribution is the same or different among two or more populations. So remember, the null is always going to be that there's no difference. So our null in this case, check the wording out, is there's no difference among the distribution of proportions, or there's no difference among the distribution. Just make sure you put that in context. And the alternative is going to be exactly like what we talked about for your goodness of fit. The alternative is that there is some difference among the distribution of proportions. We don't know. Part of the distribution could be the same and part could be different. So as long as there is one difference in the distributions, then that would be our alternative. What will it look like for a test for independence? Now remember, independence is a single sample and we're checking to see if two variables within that single sample influence each other. So does gender influence whether you take a math or a history case? So since we're checking for an association, once again, we're always assuming that there is no association or no relationship. Our null is that there's no association between variable 1 and variable 2. Notice we're not comparing the distributions here because I just have a single sample. I'm checking to see if within that sample, two variables influence each other. So our alternative is that there is an association between variable 1 and variable 2. Make sure your hypothesis is in context. So the chi-square statistic still, once again, is going to be measuring the observed counts to the expected counts. And we're going to take a look at what that looks like when we have more than a one-way table. Let's take a look at this first example. Market researchers suspect that background music may affect the mood and buying behaviors of customers. One study in a Mediterranean restaurant compared 3 randomly assigned treatments: no music, French accordion music, and Italian string music. Under each condition, the researchers recorded the number of customers who ordered French, Italian, and other entrees. So notice these are counts, okay? So what does this table mean? The entree ordered was French, no music. Entree order was French and French music, French and Italian music. Notice there were a total of 99 French meals ordered. This row would say they ordered Italian, did not listen to music, ordered Italian, listened to French music, ordered Italian, listened to Italian music. This would tell me that there's a total of 31 Italian meals purchased. Your other is the same thing. No music, purchased 43 meals. French music, the other purchased 35 meals. Italian music, purchased 35. And notice this is 113. That's your total of other types of meals that were ordered. Now also notice we have a total in our column. So 84 people did not listen to any music, 75 listened to French, and 84 listened to Italian. Now you always want to find this total right here. This is the total of the table and they should match. Your total from your column should equal the total from your rows. So when you add this, it should be 243. Add this, it should also be 243. Okay, so we're going to calculate the conditional distribution in proportions of the entree ordered for each treatment. Now, what does that mean, the conditional distribution? The conditional distribution is just taking a look at what the distribution was for each scenario. So, for example, when it says calculate the conditional distribution of the entree ordered for each treatment, what was the treatment? The treatment was no music, French music, or Italian music. So, based on the music, okay, what type of entree was ordered? So in this case, when no music was playing, so let's just look at no music. We had 30 out of 84, 11 out of 84, and 43 out of 84 for other. So that's the conditional distribution when there was no music playing. Why is that called a conditional distribution? Because the entree that we looked at is based on the condition that there was no music being played. How about French music? So when we say the conditional distribution, let's find the proportions of what it's going to be when they listen to French music. So the total here is 75. So 39 out of 75 ordered French. 1 out of 75 ordered Italian, and 3 out of 75 ordered other. Now, how about the last one? What about when Italian string music was playing? 30 out of 84 purchased French, 19 out of 84 purchased Italian, and 35 out of 84 purchased Italian or other. So just keep in mind, conditional distribution, there's a condition. The condition in this case was the type of music that was played. Then what was the entree given that condition? Now let's take a look at a graph comparing the conditional distributions. So what we're taking a look at here is whenever we played no music, what were the three distributions look like? Notice other was the highest. When we were playing French music, the French was the highest. And when we were playing Italian music, actually the other was the highest. So we're just comparing the conditional distributions based on the type of music that was played. Now let's take a look and write a conclusion. So write a few sentences comparing the distributions of entrees ordered under the three music conditions. So when we take a look at those graphs from the previous page, does the type of entree that they order, does it change based on the music that was being played? So in this case, the type of entree that customers buy seems to differ considerably among the three music treatments. If we take a look, orders of Italian entrees were very low when French music was playing, but were higher when Italian music was playing or no music. French entrees seem popular in this restaurant as they are ordered more frequently under all the music conditions, but most often when French music was playing. For all three music treatments, the percent of other entrees ordered was similar. So if you take a look, notice other was similar in all the conditions. The Italian entrees were ordered more when Italian music was playing, and the French was ordered most often or very often in all three cases. Now for this one, we are going to use the Chisquare Test for homogeneity because we're checking to see if there was any difference among the distributions. Just take a look at what the null and alternative would look like in context. There's no difference among the distributions of entrees ordered when there's no music, French music, or Italian. And alternative is that there is a difference